I've drawn here a little bit about forces. First off, how we show forces is through a free body diagram where we represent an object or system by a point, as if it's a point particle, to look at all the forces acting on that object or a system as a whole. We have in this free body diagram, we have an example of two forces. They're given by the force vector with an F on, comma, what it's by, in subscript. So the force on blank, by blank, normally given by its initials. For example, here we have the force on the ground by the shoe, and the force going the other way would be the force of static friction. Now, speaking of static friction is the friction before something moves. My hand on this whiteboard, for example, I'm pushing on it. Right now it's experiencing static friction as the friction is stopping it from moving. But now I've met the threshold that I need. I have passed that force, and I'm now experiencing kinetic friction force. The kinetic friction force is a force of friction while something is sliding across a surface. For our example here, before the foot slides, say this is someone bowling in their last step, it's a slide foot. When the foot initially goes down, before it starts to slide, they are experiencing the force of static friction going the other way, which is a force on the shoe by the ground. So if we're to give a free body diagram of the shoe, we have the force on the shoe by the earth, and we have the force on the shoe by the ground. The force on the shoe by the ground is at an angle going this way, as it encompasses the normal force, which a normal force is a force in the opposite direction from normally gravity that is keeping whatever object, in this case the person's foot, from going through into the earth. The normal force is from the ground and it pushes up to negate gravity, the force on the shoe by the earth. Then we also have the force of static friction in this, which is pushing the other way. This free body diagram, however, is not quite complete, because it should have, based off this, the shoe should be moving this way. The force we're missing here is the force on the shoe by the person. The person is pushing the shoe this way. The gravitational force is pulling the shoe this way, the force from the earth. The force of static friction is negating the person's force, and the normal force is negating gravity's force. Both static friction and normal force come from the ground, so the vector arrow on the free body diagram from the ground is at an angle. The force of static friction can only be equal in magnitude to the force that it's negating. So the force on the shoe by the person, which translates to the force on the ground by the shoe, given by Newton's third law here, must be equal in magnitude to the force of static friction. Otherwise, the shoe would have some amount of acceleration and it would be moving. There's a few different types of forces that these fall into. There's conservative forces, which are path dependent, such as the force of kinetic friction. And there are non-conservative forces, which are path independent, such as gravity. Another difference between forces is what kind of force they are as far as contact versus field force goes. The contact force must be in contact for the force to work, such as me pushing on this pen. My force pushing on the pen will not happen if I'm not touching it. I'm not doing anything to the pen here, but I am here. For a field force, something just has to be within a field that force acts. For example, the gravitational force. If you are within the reach of Earth's gravity, Earth's gravitational force will act upon you. Looking at the example of the ball being thrown in the 2D and 3D motion video, I have selected a few points, A, B, C, and D, for which I've drawn free body diagrams. Here at point A, the boulder is pushing up on the ball to negate the force of gravity as well as pushing it outward. So the force on the ball from the person is up at an angle in the positive x and y directions, negating gravity and moving the ball forward. That purple vector there is the acceleration on the ball. At point B, the only force acting on the ball, as B is in midair, is the force on the ball by the earth. At point C, the ball is on the lane, and the total sum of forces is 0. The only force acting on the ball is the normal force, the force on the ball by the lane, and the gravitational force, the force on the ball by earth. With the total sum of forces being 0, the ball is not accelerating and it will keep a constant velocity. At point D, the ball is hitting the pins, so it has the exact same free body diagram as point C, except for the pins are pushing back on the ball, with the same magnitude that the ball pushes with on the pins. That's an example of a third law force pair. They're called third law pairs because, by definition, they represent the third law. The force on the ball by the pins is equal to the negative force on the pins by the ball. And here, there is a net acceleration, as you can see by the free body diagram, going that way, and that is merely slowing the ball down.